Hi everybody, and today I'm going to be giving you a brief introduction to to how to model structural deformation and thermal abuse of a battery using Ansys tools. So some quick introduction to battery and thermal runaway. So thermal runaway in batteries is caused by some sort of external abuse that can be from external heating, overcharging, or like what I'm going to show you today, some sort of impact. This causes some internal events and specifically exothermic reactions within the battery, which cause the temperature to increase. And if the exothermic reactions, if the heat generation of those reactions exceed the rate at which the battery can dissipate the heat, then you lead to thermal runaway. So there's three main steps to model this. It is a very complicated process, so we have to break it down. So in step number one, we model the structural impact. In step number two, we capture the physical characteristics of that damaged zone. And then in step number three, we use that information for the electrochemical-thermal modeling. So for this example, I have a 6-cell battery, and what I'm using is I'm going to be using Ansys Workbench LS-DYNA to model that battery being impacted by a sphere. The sphere is given an initial velocity and just ran into the battery, and we look at the deformation caused by that. So here are the results from that simulation. You can see in the top right the displacement caused by the impact, and that's really what we're going to use to look at the damage caused by this impact and see the effects of that. So once you do have some sort of damage to the battery, this is kind of what's happening inside the battery. So in an ideal battery, you have a positive electrode, some sort of separator, and then the negative electrode. And when the battery undergoes some sort of damage, you get some sort of break in that separator, and that allows a large amount of current to pass from the positive to negative electrode, resulting in those exothermic reactions that I just talked about, which causes the temperature to go up. So there are several steps. Once we have that displacement damage to the battery, there are several steps to measure or to simulate the electrochemical thermal simulation part of this problem. Step number one is to run the thermal abuse model with the MSMD battery model turned on. And this portion is done in Fluent. And so this is one of the battery models that Fluent has. There's a few of them. But for this example, we're going to be showing you how to run the MSMD battery model. So once you have that turned on, step number two is that you simulate it until a battery stop condition is met. Several ways to define this, but the idea here is that you're looking for when the battery has lost most of its potential. So normally, one of the most common ways to model this is when the voltage difference between the positive and negative electrodes drops below a certain point, for example. After that point has been met, you turn off the electric, ohmic, and short circuit heat sources, or you turn those to zero, and you run the thermal abuse model standalone. The idea here is you're turning off those exothermic reactions. You're not looking for those anymore. And now we just want to see what happens to the temperature as a result of those reactions. The next step is that you run the thermal abuse model with a small time step. And finally, when the thermal abuse heat source terms approach zero, you can increase the time step and solve for the thermal behavior of the cells. So this is what that looks like. This is a contour of the temperature. So we can see at the point of impact, the temperature goes up, heats up the entire battery, and then over time, eventually this starts dropping back down again just due to convection. Here we have a plot of the volume averaged temperatures of each cell. So we can see that the temperatures of the cells get up to about 900 degrees Kelvin.